Hi, here we have a video on complex ions, and to illustrate what a complex ion is, let's consider an ionic compound. Let's have iron sulfate. Okay, we've got iron sulfate here, so this is iron 3+, right? Because you'll remember that sulfate is a 2- ion. So if we had this solution if you had this compound in solution, the way that the ions would exist would be like this. So here's our iron 3+ ion in the middle, and instead of them being surrounded by sulfate ions directly, they're actually surrounded by water molecules. These water molecules, one of the lone pairs on the oxygen makes a coordinate bond with the iron, and actually in this case 6 of them do that to surround the iron with 6 water molecules, and this whole complex here, that whole thing there with the iron 3+ ion surrounded by 6 water molecules, is called a complex. So that's what it is. So in this video we're going to look at these learning objectives. We're going to work out what are complex ions and have a proper definition, and that's going to involve talking about ligands, and then we have to work out the oxidation state of the metal in the complex ions. Okay, first lesson objective is what are complex ions. Let's get our picture of our complex ion up again, and we want a definition. So the definition is of a complex ion. Definition is a metal ion. It's where a metal ion is surrounded. Metal ion is surrounded by coordinately bonded ligands. Coordinately bonded ligands. Okay, ligands might be a new term. Coordinate bond is a term we're familiar with. Let's just remind ourselves first what a coordinate bond is. So a coordinate bond is where both electrons are provided by the same atom. And those electrons end up making a normal covalent bond, but the 2 bonding electrons come from a lone pair from, in this case, oxygen. Okay, so the new word was ligands, and let's appreciate what a ligand is. So a ligand is an atom, or more commonly a molecule. Right, so in our case on the left here we've got a molecule of water, which is our ligand. Quite often it's an ion. Right, so it's either an atom, a molecule, or an ion that provides the bonding pair of electrons. That provides the bonding pair in the coordinate bond. So provides the bonding pair from one of its lone pairs in the coordinate bond. Right, and the ligands surround what's usually a metal ion. Okay, so looking at our diagram on the left-hand side, this would be our ligand. Right, this would be our ligand, and for example, this bond here is a coordinate bond. That's our coordinate bond, where this lone pair here has provided those electrons to make that covalent bond there with the iron. And as it happens, is above available, but as it happens, that that lone pair, it goes into an unoccupied d orbital in the iron. Okay, so that's defined what complex ions are. And now we've also introduced ligands, but let's have a look at a few different types of ligands. We've got unidentate ligands, unidentate ligands. We've got bidentate. Right, so uni you might see would be like 1, bi is 2, so we've got bidentate ligands, and we've also got multidentate ligands. We're going to look at examples of each one of those three cases. First of all, let's have a look at unidentate ligands, and an example of a unidentate ligand might be ammonia. Okay, so ammonia we know is NH3. All right, so formula NH3. Let's draw ammonia out. So we might have a hydrogen on the plane of the slide. We might have a hydrogen coming out towards us, and you might have another hydrogen going into the page. And of course, nitrogen's got 5 electrons, 3 of which are occupied in those 3 bonds, but it has a lone pair as well, and that lone pair is the one that would make coordinate bonds when ammonia acts as a ligand, and that has 1 lone pair making 1 coordinate bond, so that's a unidentate ligand. Okay, so chloride would be another example. So chloride, Cl minus, and as you know that chlorine as an atom has 7 electrons, but when it makes chloride it gains an electron and it's got 8 electrons, so it's got 4 lone pairs, but only because of its size, it's quite a big ion, because of its size only one of its lone pairs makes a coordinate bond with a metal ion. Right, so it is a unidentate ligand because only one of its lone pairs makes a coordinate bond. And thirdly, we'll have a look at water. We saw water in the previous slide. So water, we have oxygen with 2 bonds to 2 hydrogens. Oxygen in group 6 has 6 electrons, so it's got 2 lone pairs. But again, only one of those lone pairs, I'll circle it, only one of those lone pairs would make a coordinate bond with a metal ion. Right, so it also is a unidentate ligand. Right, so we've got 3 examples of unidentate ligands, and they're unidentate because they make 1 coordinate bond. Okay, so let's move on to multidentate ligands. We're going to look at an example of a multidentate ligand, and this one's called EDTA. Right, here's a picture of it. So let's label it first, EDTA. And the EDTA stands for ethane, right? So this is the ethane part of the molecule, and the D stands for diamine. So you've got 2 amine groups, so that's diamine, and then the T stands for tetra. You see, we've got 4 other parts to the molecule, and they look like, don't they, acetic acid or ethanoic acid. So this would be 1 acetate ion, all right, and we have the 3 others on the other corners, so that's why it's called EDTA. Now let's have a look, let's change colour and have a look at all the lone pairs. So we've got a lone pair on this oxygen of the ethanoate ion. There's another one here, and another one here, and another one here. So each of the ethanoate ions has a lone pair on the oxygen that has lost its hydrogen. But there's also on the 2 nitrogens, there's also another pair of lone pairs. Okay, so we've got 6 lone pairs that could possibly form coordinate bonds with a metal ion. And 6 is more than 2, so we call it a multidentate ligand. All right, so we've got 6 lone pairs, which is potential for 6 coordinate bonds. Which is why we call EDTA a multidentate ligand when it joins up with a metal ion. Incidentally, EDTA is commonly used as a limescale remover. So your coffee machines at home, especially in London where the water's hard, would gradually accumulate limescale, and to clean it you might use EDTA, or even washing machines and other electrical goods that use water would use EDTA as their limescale remover. And lastly, let's have a look at bidentate ligand. So an example of which would be ethane 1,2-diamine. So let's write that out and then we can draw it. So ethane 1,2-diamine. Ethane 1,2-diamine, so that has the formula NH2, so it's got an amine group on one end of the molecule. It's got an ethane middle bit, like so, and it's got another NH2 amine group on the other end of the molecule. And of course, each of these nitrogens has a lone pair, which I'll draw as red dots like that. And so you can see that we've got two lone pairs that are available to make coordinate bonds with a metal ion, so we would call that a bidentate ligand. So let's draw how it might bond with a metal ion. Let's use a generic metal ion. We could call it M2 plus or M3 plus, doesn't matter. Okay, and so this ethane 1,2-diamine molecule would be arranged like this. So you would have your nitrogen with the lone pair here, making that coordinate bond with the metal ion. That's bonded not in a straight line, but in a bent shape. And this is going back into the page, right? So the lone pair on the second nitrogen is going to come from behind, right? So we're going to draw a coordinate bond with a hash line like that. So that's molecule is going back, and then the coordinate bond is coming back from behind towards the metal ion, and we can draw another ethane diamine molecule from below. Okay, so we're going to have a nitrogen with a lone pair in the plane of the slide. So we've got a coordinate bond there, and then we've got a molecule coming out towards us. And so if that molecule has come out towards us, the coordinate bond needs to go back into the page. So we can draw a coordinate bond like so. And let's draw the third one. So we've got nitrogen coming from behind, or going, yeah. So that's our coordinate bond coming from behind, and then we might have the rest of our molecule like so. And we've got the other nitrogen, which is now out of the page. Sort of this molecule is like horizontal, and so that would make a bond going back towards the slide, the plane of the slide. Okay, so quite difficult to draw in 3D. Hopefully that's, along with the words, has given you an idea how that might be structured in 3D. You're not likely to be asked to draw something like that in the exam, and we might get the Molymods out to try and construct something to get you a better idea of what they look like. But while we're here, let's introduce this term coordination number. Coordination number. Okay, so the coordination number is the number of coordinate bonds. All right, so it's equal to the number of coordinate bonds. Simple as that. All right, but in this case, you know that you can see that we've got three ligands, each of which are bidentate. All right, so we've got two coordinate bonds, 2 coordinate bonds per ligand, right? So 3 times 2 is 6. So we've got 6 coordinate bonds altogether, and so the coordination number is 6. that's the coordination number. Okay, and if you might remember on the previous slide when we had a multidentate ligand, one ligand was making 6 coordinate bonds. So again, the coordination number would be 6, but that would be constructed with 6 coordinate bonds by one ligand, so 6 times 1 equals 6. Okay, that's bidentate ligands. In fact, why don't we look at those two other examples in a bit more detail to illustrate coordination number even more. So when we had our water molecule, this was our water molecule was our ligand, and that was a unidentate ligand. Water molecule was a unidentate ligand, but we had 6 of them. All right, so we had 6 unidentate ligands, right, each making 1 coordinate bond. Right, so we have a coordination number of 6. And in the other example we looked at, we had EDTA. All right, so let's put a circle around. So EDTA, it's all surrounded by one molecule, one molecule, one ligand, making 6. So it's one ligand each making 6 coordinate bonds. So our coordination number is 6. Okay. So we've had a look at complex ions and defined them. We've had a look at ligands and defined the 3 different types of ligands. We've also defined the term coordination number. So the last thing to do in this video is to work out the oxidation state of the metal in the complex ion. So when we're looking at these oxidation states of our complex ions, we have a formula that we can work with, which is written like this. So the oxidation state of the metal ion right equals the total oxidation state of the complex, total oxidation state of the complex minus the sum of the oxidation states, of the ligands. That might not make sense yet, so let's look at a couple of examples. Here's a complex ion. So we've got a copper ion, and we've got our ligand is water, and we've got 6 of them, and the complex has a charge of 2+. And the complex has a charge of 2+. Okay, so if we want to work out the oxidation state of the water molecule is 0, that's a neutral molecule. We've got a 2+ charge on the whole thing, so that 2+ must come from the copper ion, so we can say that the copper ion is a +2 oxidation state. Okay, and let's have a look at another example. Let's use copper chloride this time. So in the case of chlorine, we get 4 ligands surrounding our, well, let's use cobalt just to be different. Let's use cobalt chloride. So our cobalt chloride complex has a 2- charge. And as we know, a 1 chloride has a -1 charge, but we've got 4 of them, so that's a -4 altogether from the chlorides. The complex has a -2, so that means that the cobalt must be +2. +2 is the oxidation state of the cobalt in cobalt chloride. And why do we name these while we're at it? So this would be, this copper complex on the left hand side would be called copper hexa-aqua complex. And similarly on the right hand side we'd have a cobalt tetrachloride complex.